Okay, second part of the dynamics chapter, that's forces and momentum. What we're looking at is the descriptive part. So this is all about how things change when things are not constant. So without going into the details of what is Newton's first, second and third laws, they're all there in the background. It's more of the overall effect and how does that describe what motion is happening at the time. So you'll have done parts of this at GCSE, some parts you may not have done, and we'll certainly pick up on some of the deeper meanings behind it. Okay, so when we look at that section, it does link into what we did about the lifts and that kind of thinking, but really it's all about that second law in terms of mathematics, bringing us to the point where we can describe what's going on. So if we're talking about effects, often it's summed up as terminal velocity. It is not just terminal velocity, there's a lot more to it. However, those cover a lot of the main ideas. So if you've done quite a lot of work on terminal velocity, crack on through this, you'll find most of this is kind of logical sense. So one thing you may not have is terminal velocity isn't just about falling objects. Okay, it is anything moving through fluids, liquids, gases, vapors, any of those where you're moving through, the forces will change with you. So again, be wary, some people mix it up with Newton's third law. It's not about that, it's changing forces. So it's all about Newton's first law. Okay, so the crucial bit is it's not simple maths. Acceleration is not constant. That's the bottom line of it. So we're going to start with Stokes' law. Now Stokes' law can be derived using a very simple experiment, dropping spherical objects into a liquid, looking at their terminal velocity. So once they have finished accelerating, so if you drop this from the liquid, it's going to accelerate until it reaches a certain point, and that can be your start point, so that's your U, and whatever large distance as possible you can get, you can measure that value from the distance and the time it took to cover that distance downwards. Okay, so that will give you your vertical velocity once it's finished that acceleration stage. Okay, so acceleration, and then sorry, I suppose that should be a V. That is a nice constant velocity. Okay, so it can be found like that. Originally it was looking at liquids and how they drip through or rather flow through a tube out of a liquid. So it's all to do with ideas of cohesion, adhesion a little bit, but mainly cohesion between layers and within a liquid, and how things move at different rates. Just like in rivers, the fastest flow is in the center. At the edges it gets, or as you move to the edges, it gets slower and slower. So it's almost like you've got parallel layers flowing along. Okay, so liquids are complex, let's say that. Now the basic idea is using empirical evidence, i.e. using data, they came up with a law that said the drag force is a value 6 pi nu. Okay, this is not efficiency, it's a different use of nu, sorry about that, and radius and velocity. Okay, so this idea of the fluid flowing gave us this. Now if we want to take that a little bit further, we can do a lot of ideas to think about how things move. So let's just link very sensibly on that experiment where we drop something through a liquid. Just to give you a bit of background, it is of course all about the forces. Okay, and the key idea is with all of these processes that we're going to do in this section, it's all dependent on the fact that if things are falling, then the force that's keeping it moving, keeping it accelerating, is your weight, mg, and you will have some sort of resistive force, and this will be your drag. Okay, that will always be true. There are no other forces. That's caused by the clashing or crashing into colliding with all the particles in the way, and this is the force that's making it happen. So this is a reaction to that action. Okay, that's what's producing the other force. Now, if we go to a basic level, that's all it is. Okay, but actually there's a little bit more complicated to it because of some of the extra bits. So this is known as the viscosity, the stickiness of the liquid, and that's obviously going to affect drag. If we put that in, then what we can say is at terminal velocity, okay, and this is our defining point, the forward, the active force, in this case the vertical force, is going to equal the drag. It won't be if it's a cyclist going along forwards in the wind, it will be the force due to them pushing on the pedals. So that's going to equal mg. Now in reality, we have real factors as well that are going to affect it. We have a little bit of an extra force as well, and I'm going to add that on. It should be from the same dot, but that's a little bit more complicated. So I just drew it off to the side. Is, as quite a lot of you put on your initial points, if something's floating, there's upthrust. If it's not floating, there's still upthrust. There's still a force upwards due to the liquid. Now, less obvious if it's air that you're going through. Okay, the velocities have to be a lot higher and stuff, but you know, in liquids, upthrust is a big feature. So actually, what we need is that weight down, subtract, because it's in the opposite direction, let's say add on negative upthrust. Okay, I'm going to put it as force still just to make it obvious. Okay, now if we do a little bit of revision, we can remind ourselves what was going on. Gravity is obviously gravity, but the mass, how do we find that? Density and volume. So density times by volume will give you mass, times by g. Okay, and upthrust, I should say, of the sphere, so I'm going to just put a little s there, so the density of the sphere, but actually it's the same equation for upthrust, except it's the density of what was there, so it's the fluid. Okay, times by volume, and again it's the weight, so equal to the missing fluid. So down is how much is there, upthrust is how much was there before you put that thing in the way. So Vg, and what we can do is we can then start to do a little bit more and bring in some of the ideas. So if we bring in our experimental stuff, we can make this a fuller picture. Now this example I'm just doing here is because there's a lot going on. Okay, there is a big basis between various bits and pieces from this. If I want to go fully, I'm going to use that and I can rearrange it. If we have a sphere, I can clear this up. I should just point out that the volume is the same and g is the same, so I'm going to take it out. So what I can do with these is I'm just going to take my densities and I'm going to multiply by g, and I'm going to multiply by the volume, and the volume is, if you think about those, 4/3 pi r cubed. So 4, I put the 3 over the whole lot, 4/3 pi r cubed. Okay, so all I'm doing is building this up. You don't need to learn this. I'll tell you why in a second, why I'm doing it, but this process is just that case of adding together forces. It's all about knowing about the forces. If we want to round it up, can pull the whole thing in. We've got 6 pi nu r v, where v is velocity, I should add, not volume. So excuse me, that looks like a capital V. Those are the capital V's for volume. These are little v's for velocity. I'm not sure why I've got 2 V's here. I seem to have been talking and writing rubbish at the same time, so apologies for that. if we rearrange that, we can work out from the terminal velocity missing bits of data. We know what g is. Obviously we have a pi, r, that's going to go to 2, that's going to cancel out, so we can get rid of one of the r's, etc, 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 etc. So what we can end up with is an equation for terminal velocity, which is everything else rearranged. So 6, I'll take that down, 6 3s are 18, well there's 4, so if I make that 2 and 9, that would work. So 2 r squared, g, almost forgot that, densities of what was there, the solid minus the fluid, and I can divide that by 9. Okay, and this was one of the crucial steps, it may seem a bit odd, but the crucial steps in the discovery of the electron. J.J. Thomson, we've mentioned before, he did work with the work on charge, but they didn't know the mass of the electron, so he actually found charge to mass ratio, something called specific charge. You know, like specific heat capacity means per kilogram. So he found the charge, but he didn't know how big it was. The only way to find out how big it was to work it through this process by measuring how we can charge up different objects. So he used the charge to charge up oil drops, and if you drop oil through air, tiny droplets, I mean millimeter or so, too small to actually measure, then what he could do was actually work this through. And how he found the radius was that, and from the radius you can work out this, etc, etc. Okay, so the key point with this is it all comes back to having a good diagram and just saying which forces add together to equal the other forces. Okay, and it's that simple. Doesn't look simple, but it's that simple if you have a nice steady terminal velocity. Okay, so at terminal velocity where you don't have any acceleration. So what happens if you do have acceleration? Well, you know, you need to bring a lot more into it. Excuse me. So it does have an effect. It does have an awful lot of effect. Stokes' law, although it was done in the 1800s, we still use a lot. The big building just by the bridge, can't remember what it's called, but just before you get to the station in Leeds, has huge funneling effects, and all the work that's been done on it to try to combat that is down to this idea of wind flow, fluid flow around objects. So, you know, the effect of the forces all comes down to that. So there's a lot of work in there, but the key thing is from an equation found experimentally, you can do stuff as long as you know about the forces. So let's concentrate on forces that do make a difference. And when we put all these together, there's a bit more work to it. So I gave you an equation in the PowerPoint. Again, you don't need to know it, but the idea was rather than drag due to a certain size object, etc, etc, if you break it down and not worry about this viscosity, we ended up where we had certain key factors that made a difference. So if we maximum velocity will change that you could get something moving at, if we can change a matter of variables around it, and they're all to do with changing the number of collisions or the rate of collisions, number of collisions per second. Okay, so how do we do that? Well, what we can do, I should say, probably stick better with molecules. You can't go wrong with molecules. Okay, so this will happen by changing the cross-sectional area, because if you change that, then you're going to hit less air. Yeah, if you are physically bigger, you are going to have to physically move more air out of the way as you move through it, for example. So it is literally, as I say, it is a physical thing. It's nothing clever. Physically moving a number of particles, sorry, number of molecules out of the way. Okay, so if you are bigger, you have to move more air to get through the air. More obvious in water because of one of the other factors. We'll come back to that one. The other big one, other than that, is the coefficient of coefficient of drag. Now, a lot of languages, like European languages, for example, they'll often talk about coefficients. We tend to use it a bit less in the UK, but it just means fraction. So it's a fractional value that determines something. So coefficient of drag is basically how much, not how much you have to move out of the way, but how well you can move it out of the way. Okay, so it's the shape, shape of the object, because, shall we say, streamlining, that kind of idea. The shape of the object, which allows the molecules to flow past. Okay, we've known about this for a long, long time. If you look at bridge supports, ancient stone bridges, they're pointed at the front and pointed at the back because that improves fluid flow. And fluid dynamics is a huge area to think about things flowing around. Relevance at the moment, fluid dynamics is now very important because it affects on how infections flow through the air. So fluid dynamicists, people who study fluid dynamics and this kind of idea, are at the forefront of the SAGE research team. One in particular is a professor at Leeds University, so she's working on advising the government on how to improve airflow through buildings, for example. So again, the shape, the internal shapes make a lot of difference on the airflow. Okay, the other one, as I just mentioned, the other two, but these are the main two. The other two, again, fairly obvious. If you try doing all of this and you try doing it in water, you'll notice it much more than if you do it in air. So the density of the fluid. Okay, that makes a big difference because it's that spacing between the particles. Between the molecules. I don't think we need to explain that. If they're further apart, it's easier to cut through them, or the gaps between them, or to move them apart. The last one's a bit less obvious, and that is basically this viscosity. Viscosity of the fluid. It's not density. Often people confuse it. But again, on a day, it doesn't matter if it's hot or cold, that will change the density of the air that you're going through. For example, the viscosity is the type of liquid, so air doesn't change, but basically it's how, let's give the proper version, how cohesive the fluid is. And a cohesive force is how well it holds together. So basically, how unscientifically sticky. Treacle is very cohesive, has big cohesive forces. It sticks to itself better than it sticks to other objects. Water is the opposite. It's not very cohesive. It doesn't actually stick together very well, but it has a good adhesive property, so it sticks well to other things, which is why you get wet. It sticks to you better than it does stick to each other. So that one's how sticky the fluid is. So all of those are major effects. The biggest ones by far are these, and one other effect that's not mentioned, and that's really because we've started with that. Velocity has the biggest effect on how many particles are hitting every second. So worth really starring that. I didn't leave much space, sorry, there. Drags the most. Okay, so by far it's the velocity that we need to think about, which brings us nicely into kind of the links behind it. So there's a bit of a background of ideas. Again, a lot of it's common sense as such, but in terms of moving through fluids, you're unlikely to change that area. You can do. Okay, cyclists could get into a more aerodynamic shape. You know, you never see Tour de France when they're all out sprint sitting upright. They're always crouched down. So again, reducing that frontal area, the amount of area that is going to hit the air, physically, you know, I mean, that's their main body section with a bit on the legs. That's how much area they've got when you're looking from the front. If you're sat upright, you're going to have a lot more area of air to push around you. Okay, more obvious here. And again, you'll have seen films, if they're flats, they're hitting a lot of air. If you go into a dive, a head first dive or feet first dive, you've got a very small cross-sectional area. You are going to go faster. What that means is things will change, but it affects your overall force of maximum velocity. So I think that's a better phrase to use to think about in your head than terminal velocity. Maximum velocity will change if you change any of those. Okay, so using this final part of the section really puts all the bits and pieces together. So if we had a falling parachutist, we could be considering about something going along on the flat, but it's easier with falling because you have that constant force downwards, so that's easier to think about. We're basically looking through different scenarios or different sections of a scenario, and you can see from the picture, not that clear maybe, but we've got no force upwards here, bit of a force, a larger force again. Okay, so basically this reaction force is building up as we have an action force. It's not a pair. So what have we got going on? Well, here we have drag equals 0. Okay, there's no drag force. Why? What does that tell us? Well, that tells us that we can't be moving at all, as our person is not moving. So if this is a parachutist, then they are just stepping out of the aeroplane. What does that mean? Well, it means the resultant, let's break it down into those steps, resultant equals mg. That's it, it's just as simple as that. So it equals your weight. Therefore, you're on maximum acceleration, which of course, using our basics we've gone before, the force accelerating it is mg. What the mass does is it accelerates, so therefore A equals g. So at the beginning that's always true, and what happens is that means that we have a very steep increase in velocity at the beginning. What is that value in change in velocity per second? 9.81. okay, and it's always that in that first position in diagram A. As we go up more, and this is where people can kind of fall into traps of going, oh, the forces are bigger and smaller, are they balanced, are they not balanced? Stick away from that. Here we've got the drag increases. Okay, why? Because it's increasing with velocity, so it's not proportional, but as you get a bigger velocity you'll get more drag. So that means our resultant force, and to save us a lot of writing I would just call that force res, subscript res, reduces. Okay, so we have mg subtract drag. Okay, D for drag. So if we get that, because force has reduced, then acceleration reduces, proportional to the resultant force, of course. F equals ma. Here we've got just more of the effect, so drag is large, and so the resultant force is small, and that means acceleration is small. Now, What does that mean? Well, we've got a continuous change as the drag increases. Our effect overall is that we have less and less effect. Our resistance is getting, our resultant force is getting smaller and smaller and smaller. So in terms of what's going on, what we're ending up with is different points on the graph, and our rate of change of velocity, in other words our acceleration, is getting less and less. So that's where you get that ever changing, ever continuously changing gradient, until eventually, unfortunately I've gone way past my diagram here, until eventually you get to the point where you reach some maximum velocity. And what is happening there? Well, you've reached that logical conclusion. Here you've got your drag equals the weight, and so because of that your resultant force is 0. Velocity is constant. Again, if you were describing it, you may want to say the rate of change or draw a bit of a sketch, but basically, yeah, we've got nothing there. So that's scenario, or point in the scenario D, that's C, that's B, and that's A. So all the time the gradient is getting less because your resultant force is getting less. How do you get the resultant force? Just add up all the forces. If something happens, like a parachute's thrown out, then that will obviously catch a lot more air. You're increasing the cross-sectional area massively, or hugely rather, not changing the mass, and so that will be much bigger, and you'll get the same effect. That creates an upwards force in reaction to this. Basically, if you add them up just the same, if D is much bigger, then the resultant force becomes negative. It works the other way, the gradient drops down. But again, it will change, the reaction will change scale. As it slows down, your parachute slows you down, your drag will also reduce. And so what you can get is that effect where there's your acceleration, then something massively important changes. You open your parachute and you get that exactly the same curve, okay, exactly the same rate of change due to the changing forces, until again you reach this stage. What's happening? Your drag was huge, but the drag gets smaller. The weight never changes. Okay, the drag depends on velocity, and that's your key point from here. Okay, so put those together. Falling or in a car, you're going to always get, for example, a maximum velocity in a car in a certain gear ratio and all the rest, and certain power engine. That's maximized by the fact that it's all to do with drag. Okay.